In Robert Nozick's 1969 article, Newcomb's Problem and Two Principles of Choice, two boxes sit in front of an agent. One is transparent. It visibly contains $1,000. The other is opaque, and it contains either $1,000 or nothing. A highly reliable predictor has already made its prediction and filled the opaque box. $1 million if it predicted the agent would take only that box. Nothing if it predicted the agent would take both. The agent now has one visible choice: take the opaque box alone or take both boxes. What is at stake is whether rational choice should follow the causal structure of a situation or the patterns that reliably predict its rewards. The predictor's work is over. The boxes have been filled. Nothing the agent does at this moment reaches back and changes what is inside the opaque box. Still, the predictor is highly reliable. Agents who take one box tend to find $1 million. Agents who take both tend to find an empty opaque box and leave with only the visible 1,000. Nozick's setup makes a single act look different depending on what we hold fixed. Hold the past fixed, and the box already contains either $1 million or nothing. Treat the choice as evidence, and the act reveals something important about which past state is likely to obtain. The physical scene has not changed. The information we think the choice carries has. This difference is easy to miss because both sides agree on the visible facts. There are two boxes. The transparent one has $1,000. The opaque one was filled earlier. The disagreement begins when we ask what a rational calculation is allowed to do with the striking correlation between a present choice and a past prediction. That disagreement becomes sharp when dominance and expected utility give opposite recommendations. The dominance principle says that if one option produces a better outcome in every fixed state, it should be chosen. Applied to the boxes, the reasoning is brief. Suppose the opaque box contains $1,000. Taking both boxes gives $1,000. Taking only the opaque box gives $1,000. Suppose the opaque box contains nothing. Taking both gives $1,000. Taking one gives nothing. In either fixed state, taking both boxes gives exactly $1,000 more. On this view, the reliable predictor is almost beside the point. Its prediction may explain why the box was filled one way rather than another, but by the time the agent chooses, the contents are settled. Two boxing adds the transparent 1,000 regardless. Evidential decision theory reaches for a different calculation. Evidential decision theory evaluates an action by conditioning on the evidence that the action will be performed. It asks not only what follows from an act in a fixed world, but what the act indicates about the world the agent is in. If the predictor is nearly accurate, choosing one box is strong evidence that the opaque box contains $1,000. Choosing both is strong evidence that it contains nothing. This is not a claim that the present act travels backward in time. It is a claim about information. If the predictor reliably anticipated the choice, then observing what choice is made tells us a great deal about what it predicted, and therefore what it put in the box. Evidential expected utility recommends one box because one boxing is associated with the $1 million outcome. Now the paradox has its cleanest form. Dominance says take both. Evidential expected utility says take one. Each argument seems to use a principle that is hard to abandon. The strongest objection to the dominance argument is that refusing to act on a reliable correlation can repeatedly select the lower payoff option, and we will face that objection in full when causal decision theory tries to separate correlation from control. David Lewis defended causal decision theory in Causal Decision Theory, published in 1981. Causal decision theory evaluates an act by its causal consequences rather than by every event correlated with it. The distinction is exacting. An action can be evidence that something is true without being a cause of that thing. In Newcomb's problem, the choice and the contents of the opaque box are correlated. The predictor made its earlier decision by anticipating what the agent would do, but the present choice does not causally alter the earlier filling of the box. For Lewis's approach, that temporal and causal order matters. If the box is already full, taking both yields the $1 million plus the visible 1,000. If it is already empty, taking both still yields the visible 1,000. Causal decision theory therefore recommends taking both boxes. It does not deny the correlation. It refuses to treat the correlation as if it were a causal route from the agent's hand to the contents of the opaque box. This is where the strongest objection lands. Evidential decision theorists argue that this refusal can systematically select the lower payoff option. The predictor is highly reliable. 1 boxers tend to receive the million. 2 boxers tend to receive only the 1,000. A theory that insists on 2-boxing may preserve a causal principle, while repeatedly directing agents toward the outcome that, by its own lights, they have every reason to expect will be worse. The objection does not say that correlation is causation. Its point is more demanding. A decision rule must live in a world where reliable correlations can be useful, even when they do not describe direct causal control. If a rule tells an agent to ignore the very evidence that tracks reward, evidential decision theorists say the rule has failed where decision is supposed to matter, in choosing well. The dispute is now precise. One side fears treating evidence as causal influence. The other fears treating causal purity as an excuse to disregard dependable information about payoff. Judea Pearl's causal models provide a way to show why these sides calculate different probabilities without merely repeating their conclusions. Judea Pearl developed the do operator in causality, first published in 2000. The expression do X represents an intervention that sets X, rather than merely observing that X has value X. This distinction separates 2 questions that can look nearly identical in ordinary language. One question is observational. If we see that an agent takes 1 box, what should we infer about the opaque box? Given a highly reliable predictor, the answer is clear. Seeing 1 boxing is evidence that the predictor expected 1 boxing, and that the opaque box contains $1,000. The other question is interventional. What happens if we set the choice to 1 box or 2 boxes? In a causal graph, intervening on a variable removes the influence of its incoming causal arrows for that calculation. We do not merely observe a choice that arose through the ordinary pattern. We treat the choice as set. That is the mathematical shape of the disagreement. Evidential decision theory works with the probability of box contents conditional on seeing the act. Causal decision theory works with the probability after an intervention on the act. These are different operations because they answer different questions. In Newcomb's setup, the choice is correlated with box contents through prediction, but it does not causally alter the earlier filling of the box. An observation of 1 boxing points backward through the predictor's earlier forecast. An intervention that forces 1 boxing does not alter that earlier forecast. Pearl's distinction does not simply declare a winner. It clarifies why 2 apparently reasonable calculations diverge. But there is a problem with treating the agent's choice as only an isolated variable. A predictor might not merely forecast the visible movement toward 1 box or 2. It might model the very decision procedure that generates that movement. Eliezer Yudkowsky and Nate Suarez proposed functional decision theory in a 2017 paper of that name. Functional decision theory treats an act as the output of a decision function that a predictor may also model. The focus shifts. Instead of asking what follows from setting the immediate choice by intervention, it asks what follows from the output of the procedure that produces the choice. This matters because a highly reliable predictor may have modeled that procedure earlier. In that framing, the predictor's forecast and the agent's later action are not merely 2 correlated events joined by a mysterious coincidence. They are outputs connected to the same decision function. The agent does not causally change an already filled box. But the predictor's earlier model and the agent's later choice can still align because each concerns the same procedure. Functional decision theory therefore changes the description of what is being chosen. The object is not simply a hand movement at the final moment. It is the output of a decision function that another system may have anticipated. A different shift appears in performative prediction. Juan Perdomo, Tihana Zrnic, Celestine Mendler-Dünner, and Moritz Hardt introduced performative prediction in 2020. Performative prediction formalizes cases in which deploying a model changes the data distribution that the model later encounters. Here, the model's output does not merely reveal a pre-existing pattern. Its deployment can reshape the later world from which its next data arrive. Unlike the original Newcomb setup, performative prediction can involve a real feedback path from a model's output to later outcomes. That difference is decisive. In the 2-box problem, the predictor filled the box before the visible choice. In performative prediction, the model can enter the world and change the distribution it is later asked to describe. The next test is not a sealed box, but a real prediction system, where a past correlation can be mistaken for an account of what intervention would change. In a 2019 science study, Ziad Obermeyer, Brian Powers, Christine Vogeli, and Sendil Mullainathan examined a widely used US health risk algorithm. The algorithm used healthcare costs as a proxy for health needs. That choice turned an observable pattern of spending into a measure meant to stand for something else. The study found that, at the same risk score, Black patients were substantially sicker than white patients. Unequal spending had distorted the proxy. The score did not simply register health needs, it registered a history in which healthcare costs and health needs did not line up equally across the patients being assessed. This is Newcomb's problem without the theatrical boxes. A model can discover a reliable association. It can predict costs from prior patterns, but a prediction based on past correlations does not by itself identify what would happen if care, spending, or eligibility were changed. That is the practical division Pearl's framework forces us to make. Are we observing a pattern produced by an existing system, or are we considering an intervention that alters the system itself? The first question can support prediction. The second requires a causal account. Confusing them can turn a proxy into a verdict. Newcomb's problem begins with $1,000 in a transparent box. It ends with a question about models that classify people, allocate attention, and shape later data. When a forecast guides an intervention, what exactly is it forecasting after the intervention changes the world? Subscribe for more philosophy connected to the systems that govern ordinary decisions.